for this problem, we have this circuit. It's an operational amplifier circuit. We're asked what is the phase of the voltage gain in degrees at a frequency of 5.6 megahertz. We can assume the op-amp is ideal, and we have these resistor and capacitance values here. Well, if we look at the notes linked below the like button, we are going to see that this is very similar. In fact, it is an integrator. So if we just come into the notes and we look up integrator, we're going to see right here this. And it's the same circuit as we have here. And we have the kind of graph diagram of what this would look like. It goes down by -6 dB per octave. And we have our log scale and our dB, which is the gain right here. So for this, we have some formulas right here. And we want to find in the frequency domain. So we're going to use this lower one right here. So with our frequency domain, we are going to have a negative out in front. We are then going to have our 1. And when we want to convert to the frequency domain, because we have imaginary numbers here, this is in rectangular form, we want to convert to polar form. And there's more about this in the EEE 117, which is network analysis playlist. And that is somewhere on the channel, but it's in the playlist section. But we have 1, and then to convert this to the phase, we're going to have an angle of 0 degrees. And then next, and we'll go over the formulas for that in a second. We have 1, 0 degrees, and then we have minus, we have 0 for our real number. And then we are going to have some phase right here. And the way we would calculate our magnitude, which is the real number, which is this number out front, is we would say that our mag is equal to the square root of our real number squared plus our imaginary number squared. And the tangent is the arctangent, so this is the phase. The phase is equal to tangent -1. And then here we have our imaginary number over our real number. Now, there is a problem though. So for this bottom part, our real number is 0, and we can't really divide by 0. So what we're going to want to do is have our imaginary number, and we are going to divide it by something super small, basically 0. And that's how we can kind of bypass that. So we have our j omega RC. That is essentially what we're plugging into here. Our j is just the imaginary number. That's the basically I right here. Our omega, we know w, or the omega, is equal to 2 pi f. And our frequency is 5.6 megahertz. So into a calculator, we're going to plug in 2 pi times our 5.6 times 10 to the 6th. And then we have our r, which is 6.1 k. And then we have our c, which is 2.2 p. And the p is for pico, and pico is 10 to the -12. Now we are going to plug all of this into a calculator, and once we're done with that, we are going to get approximately 0.47219. Okay, and so now we need to plug this back into here. And so we have tangent -1, so the arctangent of 0.47219 divided by 0.00000001, something super small. And if we do that, we are going to get 90 degrees. So we'll come back up here, and we have 90 degrees inside of here. Now, when we do this division right here, we're going to subtract the real numbers, but we don't care about the magnitude in this case. So we're not even going to look at this part. But we are also going to subtract the denominator from the numerator angle. And if we do this, we are going to get, inside of here, a negative because of this negative, and then we have a -90 degrees. And so the negatives make a positive, and so our answer is going to be 90 degrees. And that's how we would solve this integrator. We have other problems that we're going to look at which have integrator with a finite DC, which are slightly different, but this is how we would solve this simple integrator.